These two devices may not look similar, but they both perform the same task, controlling an electrical motor. In this video, we will focus on relay logic, and this combination starter is a good place to begin. In a future video, we'll be dealing with the PLC. At the heart of the combination starter is the motor starter relay. A motor starter is a large relay that is designed to take the additional voltage and current required to operate an electric motor. Depending on the activating coil used, it will allow a smaller voltage signal to control the full voltage current of the motor. It only has one purpose: control the motor. Since a combination starter has all the elements needed to run an electrical motor, it's likely the best place to begin. However, looking at its electrical control wiring diagram, it may not be so simple after all. Everything involved in the starter operation is shown. A lot of thought and effort goes into the details, trying to show the device's physical locations as much as possible. Relay logic diagrams do not show the physical locations, just the control the device is shown. The stop-start push-button control may be physically many meters away from the motor or motor starter, and be in a conduit containing other circuits. The diagram only shows the motor's wiring. Notice here that the overload protection contacts are located after the motor starter's coil, and therefore is switching the load side of the circuit. Furthermore, relay logic drawings do not indicate the current activity status of any component, but rather its shelf state or de-energized state. To determine how the circuit works, you must read the drawing starting from the left power rail of each rung and work your way towards the right power rail. Power must flow through the control devices and the motor coil and its overloads to reach the other power rail. If all the devices between the rails are active, then the output will be energized. Notice on the right rail, an R2 is written below motor 1. This is the cross-reference where the coil's contacts will be found. In this case, R2 signifies rung 2. When the start push button is pressed, current flows through rung 1. Current flows through the stop push button, the now closed start push button, the M1 starter coil, and finally the motor overloads to complete the circuit. Once current flows through the M1 coil, the magnetic field pulls the armature to close the starter's power contacts, starting the motor, and the normally open control contacts also close, shorting out the switch, allowing the motor to continue to run. This means that M1's normally open control contacts in R2 latches or seals in the circuit, even if the start push button is released. When the stop push button is pressed, the circuit is opened and current flow through rung 1 is completely interrupted. Once current flow through the M1 coil stops, the magnetic field collapses. This causes the armature to spring back to its normal position, forcing all the linked contacts, both power and control, to return to shelf state, dropping the latch. When the power contacts open, the motor stops. The motor cannot restart without another press of the start push button. All relays must be hardwired. In order to reduce confusion and assist in troubleshooting, terminal strips are used. The first wires to be terminated are line 1 and line 2, since they will do the bulk of the work. To facilitate this, hard jumpers are used to interconnect the different rungs of the logic to act like morettes and provide multiple landing points on the terminal strip. The picture shows the terminal strip laying horizontally. This is done to facilitate the PLC. Terminal strips can be installed horizontally or vertically, but the drawings will always show them vertically. When it comes to the wiring, wires are always numbered sequentially, but they follow the drawings, so sometimes numbers may be missing. Using terminal strips keeps all the wire terminations organized and close together. Most modern machines have one or more control panels. Some electrical controls are installed remote from the panel elsewhere on the machine. To identify these remote devices, hash lines are often used for external wiring leaving the panel. Each of the panel's wires themselves are identified by the terminal on the strip. For example, wire number 15. If you see a broken set of chevrons, that usually indicates that it is continued on a different page. In this case, it's saying page 4. You can clearly see here that the relay ladder logic bears little resemblance to the physical wiring shown on the terminal strip. Let's take a look at a simple relay logic control used on a bandsaw. On the bandsaw, it's going to have a normally closed latching contact. When the operator starts the saw, it begins to fall due to gravity. The fall, however, is controlled by a hydraulic cylinder acting as a controlled brake. A valve restricts the oil flow so it goes down slowly and smoothly. Once the cut is complete, the saw settles on a limit switch. This stops the saw from running. This is the relay logic that controls the bandsaw's sequential action as shown in the video. Notice the 24-volt DC e-stop signal to the PLC. Often machines will need to work with other systems and will need to use either different voltages through transformers or entirely other sources. The 24-volt DC will come from the PLC. Normally an isolation relay will be used in this, and in this case the stop push button provides a set of dry contacts. Here is another example of some simple relay logic. It is a high-level warning alarm. If the liquid being monitored rises too high, an alarm will sound notifying maintenance. When float switch 1 is made, the warning horn sounds and the maintenance staff comes running. However, having the horn on while trying to troubleshoot and fix the problem would likely hinder concentration. So the normally closed contacts of CR1 is used to open the horn circuit. When the silence push button is pressed, CR1 is energized and seals in, opening the normally closed contacts and silencing the alarm. This is an example of NOT logic, whereby a positive action is used to defeat or NOT out another action. We will cover NOT logic in a detail in a later video. Let's look at a summation of relay logic and some of the pros and cons related to its use. On the plus side, relay logic is an effective, direct-wired solution to control many small machines and processes. It is set up in a ladder format that represents the logical sequence of the machine, and it's understood by most electricians since it uses universal symbols that illustrate the intention and purpose of the devices used. However, on the downside, there is a high installation and maintenance cost. It relies on manual printouts, and troubleshooting time is consuming, especially if those printouts are not kept up with any changes. Each relay's contacts must be checked for use and may appear on many pages. And finally, relays are electromechanical devices that will wear out.